Hey everyone. So we're still in the process of quantifying the uncertainty around Trump's support prior to the 2016 election based on the ABC News Washington Post poll. And specifically in this video, we want to go through the process to compute confidence intervals based on the standard error that we computed in the previous video. Okay, but before we get to that, I just want to briefly go back to the last slide from the previous video where I made a tiny mistake when I went through how we compute the variance of the sampling distribution. I was a little bit confused for a second because we had our equation or formula for the variance, and we pulled out our 1 over n, which of course turns to 1 over n square, and then we simplified this to the variance of x divided by n. And I mistakenly said that this should be n square and n square here, which is not the case. The slides are perfectly fine and are correct the way they are. Of course, the reason why that is the case is that here we have the variance, the sum of the variances of xi's. And as I mentioned in the previous video, xi is independent and identically distributed. Okay, so the sum of n variances is just n times that variance of x. Okay, so that means we're left with 1 over n squared times n times the variance of x, which of course n divided by n squared cancels out, and we have the variance of x divided by n. So the way this was on the slides is perfectly fine. I was just, as I walked through it, missed that step of replacing the sum by a product times n. Okay, so all these values are fine, and accordingly these values are also correct. Just wanted to make sure I correct my error in that previous video. All right, so after we have that out of the way, we're going to go back to computing confidence intervals, right? And I want you to keep in mind when we talk about confidence intervals and when we talked about the standard errors, we're always kind of talking about characterizing uncertainty in our estimator beyond our specific sample, but we're talking about uncertainty in the sampling or variation in the sampling distribution, which is again a distribution over hypothetically repeated sampling and hypothetically repeated data generating processes, right? So this is a little bit difficult to kind of wrap your head around at first, but it's really important to kind of get the underlying conceptual idea. We're always talking about variation in our estimator over hypothetically repeated sampling, okay? And the confidence interval, which we're going to talk about now, helps us characterize the uncertainty over these repeated sampling procedures, right? So from the central limit theorem, we know that for a sufficiently large sample size, that x bar, our estimator that we talked about in the previously, is distributed normally with an average of the expectation of x, which is we talked about unbiasedness in the previous video, and the variance, or the variance being equal to the variance of x divided by n, or that's essentially that's the variance in the standard in the sampling distribution. Okay, so we in the last video, and I can go back to the slides, we derived the variance of the sampling distribution, and we derived or we talked about x bar being unbiased, and therefore the average of the sampling distribution, or the expectation of the sampling distribution, is equal to the true population parameter, right? So that means, given the central limit theorem, x bar, the distribution of x bar, if the sample size is large enough, then the distribution of x bars across samples follows a normal distribution with the expectation, or the average of the expectation of x, or the true population parameter, and the variance of this distribution can be described as the variance of x, that's the individual random variable, divided by the sample size. Okay. And I guess I should say this is kind of where oftentimes this confusion comes in. The variance of x here, this is the variation in the individual x's as kind of the underlying random variable, and variance x divided by n, that's the variance of the sampling distribution when we're looking at kind of the distribution of x bar over repeated samples. Okay, so that's where this dividing by n comes in, right? So in our current case, of course, we have x bar following a normal distribution where the expectation of x is equal to the true population proportion of Trump support, that's p, and the variance of x. X is, of course, a binomial random variable, and that's p times 1 minus p. Okay, that's the distribution of our binomial random variable. The variance of our binomial random variable. Or essentially the variance of one single Bernoulli trial, I mean, depending on how you think about it. The next step in the process of computing the confidence intervals is to choose the level of confidence for our interval. The standard here is usually a 95% confidence interval, and I'll talk in a second about what this 95% coverage ultimately, or the 95% confidence ultimately means, okay? Specifically, we will compute an interval which ultimately contains, it's an interval around our point estimate based on our individual sample, right? And this interval over repeated sampling will contain the true value 95% of the times over repeated data generating processes. And again, it's a little bit tricky to kind of wrap your head around the underlying logic, because this does not imply that we have a 95% chance that the true value is within our specific interval. We're still thinking about this in terms of repeated sampling, right? The 95%, and I'll show you a visualization in a second to kind of show what exactly that means, right? The true population value is out there, we can't observe it, right? We have one specific sample with an average, or with our estimator, and we now kind of characterized the variation in our estimator across repeated sampling. And now this 95% confidence interval provides basically an interval around our specific point estimate, okay? And this interval is constructed in such a way that if you basically constructed the same interval across all our repeated samples, then 95% of those repeated samples would contain the true population parameter, right? And this seems like a subtle difference, but it's an important one. That does not mean necessarily that the probability that our individual confidence interval for our specific sample has a 95% chance of including the true value, right? It's a different statement. The true value, you can think about it this way. This is the 95% is purely a statement about the repeated data generating process, and 95% is just the proportion of times that this interval contains the true value or not. For any one specific interval that we computed, basically there is no probability this true value, this interval either contains the true value or it doesn't. So in that sense, it's either 0 or 1. But over repeated procedures, over repeated samplings, we can say, okay, 95% of the time, it will include the true value. Okay. It's a little bit difficult to wrap your mind around this, but we'll go through a visualization that kind of makes that point a little bit more clear. Okay. So in order to compute this confidence intervals, we will basically compute, so for a given alpha level, so for example, for alpha equal to 0.05, we can compute the 95% confidence interval, which is 1 minus alpha times 100%, as basically the interval of where the lowest value of the interval is x bar minus a critical value for that specific confidence level times the standard error. And the upper bound of that interval is x bar plus our critical value z for our confidence level alpha times the standard error, right? So we have our standard error, which is basically the standard deviation of our sampling distribution. That's our standard error. That's the deviation across samples, right? And now, based on our confidence level, we choose a critical value that is multiplied by times the standard error, and that product will be added or subtracted from our x bar, from the kind of center of the distribution, to compute our confidence interval. Okay. For different confidence levels, we have different critical values, and you've seen some of those before. Given that z follows a standard normal distribution, and make sure to check out the video on normal distributions as well, if you kind of need a refresher on that as well. For a given confidence level, we have different critical values. So, for example, for the 95% confidence interval, which means alpha is 0.05, our z value is 1.96, right? And 1.96 will probably sound familiar to you in the context of our standard normal distribution. We talked about how 95% of the probability mass of a standard normal distribution is within minus 1.96 and plus 1.96. So in a standard normal distribution with a standard deviation of 1, 95% of the probability mass is between minus 1.96 and plus 1.96, right? And that's exactly the same logic that we're basically using here to compute the confidence interval for a given estimator. We're just multiplying these same critical values, 1.96, or for 0.1 confidence level, or 90% confidence interval, it's 1.64, times the standard error of that distribution to ultimately get our confidence interval for 95% or 90% or 99% of the probability mass. Okay, and again, we have to be careful about the interpretation of these confidence intervals, right? As I mentioned, the probability that the true value is in a particular confidence interval is either 0 or 1, right? For one specific confidence interval that we compute, the true value is either in there or not, right? Since we're kind of thinking about this in frequentist terms, right? This interpretation of confidence intervals is very much in this frequentist interpretation of probability. One specific confidence interval of one individual sample is either includes the true value or it doesn't, right? When we talk about the probability, or this 95% confidence, we're talking about this 95% confidence over repeated samples, okay? So the 95% probability is the 95% probability over repeated samples that 95% of the confidence intervals include the true value, not that one specific confidence interval includes the true value, right? So in other words, our confidence intervals are random. They change, across different samples, but the true value is fixed. It's in the population. It's a true specific value, right? So we can't really make from a frequentist perspective, we can't really make a probability statement about the true value being in a confidence interval versus or being in a particular confidence interval. We can only make a statement about over repeated samplings, how many of those confidence intervals would include the true value, okay? So now going back to our ABC and Washington Post poll, we can compute the confidence intervals for those polls using the equations that we have up here and the critical values for 95%, 90%, and 99% confidence intervals. And again, we take our average x bar and we subtract our critical value times our standard error to get subtracted to get the lower bound of that confidence interval and added to get the upper bound of that confidence interval. Right, so the 95% confidence interval for our Trump support based on the ABC Washington Post poll is 0.409 and the upper bound is 0.451, right? So again, that does not mean that we have a 95% chance that the true value is within that specific confidence interval. Rather, the interpretation is over repeated samplings. If we repeated the survey again and again and again, we computed our estimator, our average Trump support, and we computed our confidence interval based on the procedure that we outline here, then 95% of the confidence intervals that we compute will include the true value. Okay. To kind of further drive home that point, which again seems a little bit kind of tricky to wrap your head around, but it's important to kind of keep in mind that these are always statements about repeated sampling and distributions over repeated samplings and not particularly on one specific sample, right? So what we have here is kind of what I did here was I wrote a quick simulation. The code is on RStudio Cloud as well, so feel free to check that out as well. What we have here is a simulation of 100 repeated samples of Trump support with n being equal to 2,200, so similar to the ABC Washington Post poll. We have our true population parameter, which is of course 46%, I think it was, for Trump. So that's the actual election result. And what I did basically was simulate 100 repeated samples, just each one just like the Washington Post poll, and then computed the average for that sample and computed the confidence interval based on the formula that we have up here, and then plotted the confidence interval for each individual sample. Okay, and what we see here is basically the distribution of x bars. That's the distribution. That's essentially our sampling distribution over repeated samples. Right. This is our hypothetical scenario where we could repeat our sampling procedure 100 times, and we basically have gray, or we have bars for the 90% confidence intervals, and these are in gray if the 90% confidence interval includes the true population value, and it's black if the 90% confidence interval does not include the true population value. Okay, and the key thing here is to kind of again go through that logic, right? What we have in our specific case is one individual sample, right? One individual sample with one x bar and one confidence interval. Suppose that would be this one. That looks pretty much on point with regard to the results in the ABC Washington poll. And the 90% is not a statement about whether about the chance that this individual confidence interval includes the true population value, but rather we look across our 100 or maybe 1,000 repeated samples. We look at how many of these confidence intervals include the true population parameter and how many do not, right? And so for the 90% confidence interval, what we can say is that around 90% of the confidence intervals will include the true population parameter. Here we have about 100 samples, so 1, 2, 3, 4, 5, 6, 7, 8, 9. Of our 100, 9 did not include the true population parameter, right? So the 90% confidence interval tells us the probability, the proportion of repeated samples whose confidence interval includes the true population parameter, which is different from the individual probability of one specific confidence interval, including the true population parameter. This specific confidence interval doesn't include it. This one does, right? This is 0 or 1, but across repeated samples, 90% of them do, okay? And that's basically the key to understanding how to interpret confidence intervals, okay? There's a really great visualization that I linked on Canvas by Harvard grad student Sophie Hill, who basically wrote a little Shiny app in R that allows you to kind of do the same procedure that I did here with my code, where you can vary look at different population values, different confidence levels, and kind of simulate, and different sample sizes, and simulate your own kind of sampling distributions and kind of play around with this confidence interval interpretation to get a better understanding of what is going on. So please check out this this awesome visualization as well. It's linked on Canvas. Okay. So lastly, last part is to bring this back to the margin of error in polls. Okay, so this is something that is that I mentioned early on in the previous video. That was kind of an additional piece of information about that specific ABC News Washington Post poll. And this is something that you see usually conducted or usually added as an additional piece of information with any poll that is published, right? And so what is this margin of error in polls? And essentially this margin of error in polls usually describes the deviation in a 95% confidence interval, right? So usually this margin of error in polls is basically plus or minus, this is the critical value for the 95% confidence interval times the standard error. So plus or minus 1.96 times the square root of, in this case we have in a close election, which means that the probability, the true population proportion is around 0.5. So 0.5 times 1 minus 0.5 is just 0.5 times 0.5. So that means the margin of error in a close election, where the probability is around 0.5, the success probability, is usually around plus or minus 1 divided by the square root of n. Okay, so there are two things. Of course, the margin of error decreases as the number of as the sample size increases. Okay, that's one important point here. Of course, that makes sense. The larger the sample, the lower the uncertainty. But another key point that is often overlooked is that this margin of error also depends on how close this election is. Okay, so basically for a very close election, the margin of error is much higher. If we have a not so close election, this 0.05 times 0.05, or the square root of 0.05 times 0.05 actually becomes smaller, and therefore smaller than 1, and therefore the total margin of error actually becomes larger. Okay, so for example, in a typical poll with using kind of this formula for close elections, we have a margin of error around 2.9 percentage points. And again, this is very much related to our discussion of the confidence interval. This is basically just the deviation that we subtract or add to our mean value in order to compute the 95% confidence interval, right? And that's around 2.9 percentage points in a poll with 1,200 respondents. in our ABC News poll, we have around 2,200 respondents, so the margin of error is around 2.1. In the actual poll, I don't know exactly what kind of additional adjustments they made in their computations, but their actual poll says plus or minus 2.5 percentage points. They might take into account additional sources of uncertainty here, but just based on the sample size, this would be plus or minus 2.1 percentage points. And of course, that means we can also use this information to plan data collections, right? So if we want to run a survey and we want to know, okay, what sample size do we need in order to achieve a certain level of a certain sufficient margin of error that is sufficiently small in order to, for example, call an election. Of course, we can kind of solve this for n, so multiply by n, divide by the margin of error, and take the square. And then we have our approximate sample size as 1 divided by the margin of error square. For close elections, if we want to compute this for any type of election, we, rather than just assuming 0.05, can plug in p times 1 minus p, of course. Okay, so that means we need a larger sample when p is close to 0.5. So for a very close election, we need a larger sample in order to achieve the same margin of error, or in other words, the margin of error increases as the election gets closer. And we could, for example, say what is the minimal sample size required when the probability is very far away from 0.5. So what about success probability of 0.3? Then, for example, in order to achieve a margin of error that is just equal to 0.03, so very small, we just need a sample of 900 observations, right? So this is just one example where with elections that are not so close, the margin of error, you can actually achieve a much smaller margin of error with a much smaller sample size. Okay, this is just one illustrative example to kind of make that point. Okay, so this is how the margin of error in polls is related to our kind of confidence interval argument. Okay. I think I'm going to take a quick break here, and in the next video I'm just going to give a quick summary of inference with random sampling.